So welcome to the Google Algorithm Seminar. Today we're happy to have Sandeep to give a talk. He's now a fourth-year PhD student at MIT, working with Piotr Indyk. He seeks to work in the sweet spot between theory and practice. Recently, he has been working in the intersection of ML and classical algorithms to design efficient algorithms for large datasets, as well as using ML to inspire algorithm design. So please welcome our speaker.
Yep. Thank you for having me, and that was a nice intro. But I also wrote that intro, so that's why it sounds so nice. but okay, so I'll talk about faster linear algebra for distance matrices. This is joint work with my advisor, Piotr Indyk. And at any point, please feel free to just shout out an answer, or shout out a question and any concern you have. I totally don't mind. And I made this presentation a bit short so that we can, if people have questions, we can answer. Okay, cool. So the outline of the talk is, first, I'll talk about some motivation, what's the point of this presentation and this work. And then I'll talk about some upper and lower bound results on something called matrix vector products for different distance functions. I'll give some experimental results. And then if I have time, I'll talk about how to construct distance matrices faster than you think, I guess. Cool. So, what's the point? I definitely won't be able to answer, the point on this cartoon. That's like beyond the scope of this talk. But maybe we'll touch upon this, like if we're all doing deep learning, what's the point of theory? Maybe I'll have something to say here, or maybe I won't. But anyways, what's the point of this particular talk? The point is we want scalable algorithms for distance matrices. So let me just lay out some foundation. So let's say we have a data set X of n points in R to the D, and we have some distance function that we're interested in among these points. And throughout the talk, it will be like L1 or L infinity or L2, these common LP norms. And the central object of this talk is this distance matrix A, where the I and jth entry of this matrix is just the distance between xi and xj. Okay, so that's the key object of this talk. And these matrices are interesting because there are dense matrices, right? Unless points are the same, most of the time they're dense matrices. And a lot of times in the real world, dense matrices don't really show up. But this is actually one of the few classes of what I think natural dense matrices that show up. And they show up in many, many places, from like clustering or non-linear, or like visualization, dimensionality reduction, and a whole host of other places. But one kind of concern is that they're very expensive to use and store, right? They need, if you initialize this matrix and if you have endpoints, then you need n squared time to create this matrix at least, and also n squared space, right? So this, for a large number of points, this is very, very expensive. And so the motivating question of our work was, can we do better? So our angle of attack on how to make things better is we're going to create fast algorithms for matrix vector products. So first, as a definition, what is a matrix vector product? Basically, we feed in a vector y, and it outputs a times y, where a is our distance matrix. This is like the key subroutine that we want to get something for. And why is this like a natural thing to look into, or natural like point of attack? Because many algorithms in linear algebra and in other cases, they essentially only work through matrix vector products. For example, think about power method for finding the eigenvalues, or how do people solve linear system in practice? They all just use matrix vector products, and in general, lots of iterative methods only access the matrix via matrix vector products. So this is like a very nice abstraction to work with. And another line of sort of interest in matrix vector product is that there have been many recent and classical works that sort of characterize how many matrix vector products do you need for various tasks, like let's say finding the eigenvalues and eigenvectors. That's the classical power method, but also more complicated tasks like finding low rank approximation of the matrix and so on. So I guess my pitch to you is that, if we have fast matrix vector products, then we automatically get many, many fast downstream algorithms. So matrix vector products is like the star of the show. We need to, if we understand that better, then we can get a whole host of things for free. So now let me talk about our results. So let me start with one of our upper bounds. So the first upper bound result is a very short and sweet matrix vector product algorithm for exact L1 distance matrices. So what does that mean? First, our distance matrix will be the L1 distance matrix. This is a very natural distance function. And what we'll get is a way to compute a matrix vector product of this matrix without ever constructing this matrix. And it will be an exact algorithm. So the main theorem is the following. We have access to our data set X, the points. And for any query vector Y, we can compute A times Y exactly in linear time, n times t. Remember, n is the number of points, t is the dimension. And it needs some like almost linear time pre-processing, but that only needs to be done once. So this is very nice and a bit surprising, but it turns out this the algorithm is very, very simple and like very easy to present here. And some of the techniques here also apply to more complicated functions, but I won't really talk about them. So a counterpart result is now we have a bunch of upper bound results for fast matrix vector products, like we saw this for this L1 case. Is it true that all natural distance functions or all natural LP norms admit fast matrix vector products? And surprisingly, the answer is no. And in particular for this L infinity norm, meaning the ijth entry of A is the L infinity norm of xi minus xj, you can actually prove that any algorithm that computes a matrix vector product needs n squared time. So this is kind of saying that only thing you can do is just create the matrix and compute it in the usual way. Sorry, someone. Oh,
is this an unconditional lower bound?
No, it's not an unconditional bound. It is a conditional lower bound. Okay. It will reduce to something called set, which I'll talk a bit about later.
Yeah, thanks.
And this is also interesting for another reason, I think, which is there's another really well-known problem called nearest neighbor search, and there you can get fast algorithms for L1, but not for L infinity. So there's like some separation there, and there's also some separation here, which I find kind of interesting. But they're not related, I think. But still, the separation exists. And now this is more for fun. Like so far I've been sort of harping about things are efficient, they're useful. But now this is like this. The next series of results is like not really useful. No one should actually implement this, I think. But it's fun, so that's why I'll talk about it. So next question is, what is the fastest way to construct an approximate distance matrix? Say for the L2 case, where the ijth entry is the L2 norm of xi minus xj. Right. So if someone had asked me this like a couple of months ago, or however long ago before I worked on this, I would say, okay, first, if we want to create the matrix, then we at least need n squared time. That's a strict lower bound. But we can do n squared log n if we use something called the Johnson-Lindenstrauss lemma. And basically how that would work is there's a lemma called the JL lemma, which says you can first project all your points to log n dimension, and all the distance will be roughly preserved, and just make the matrix using the representation from the projected dimension. And that takes n squared log n time. And it seems like this is probably the best you could do. But actually, very, very surprisingly, you can actually get, instead of n squared log n time, you can get n squared roughly log n time, which is a bit surprising, right? It's sort of like saying, if you could project into log n dimension and compute the matrix there, that's like the roughly at runtime. But there's no dimensionality reduction to go that small of a dimension. Like that's just impossible. But somehow you can still get a better version than than what the Johnson-Lindenstrauss lemma implies. And I find this interesting, not from like a practical viewpoint, but just from like maybe a philosophical viewpoint, because sort of in many algorithm subroutines, that one of the main use cases of JL lemma is to compute a bunch of distances, right? Or to compute the distance matrix. And somehow you can do much better if that's the task you care about. Okay, so now let me go back to the first result I talked about and give you like a very, very short proof of it. It's very simple, but just to remind everyone what I promised, which is we can compute A times Y for where A is the L1 distance matrix exactly in linear time without ever creating the matrix, if we know what the points are. So for the proof, let me demonstrate the algorithm, and I'll consider a very special case where the query vector is all once vector. It doesn't really matter, like this is just for clarity, but like the same idea works for any Y. So the first question to ask is, what is the kth entry of A times Y, right? If you just think about what the row of A looks like, it's this sum where we fix the first xk and then the xj varies, right? This is a row, and we add every entry of this matrix along the row, kth row. Right, so let me just, what is the first thing to do that we can do? Okay, let me just expand what this L1 norm definition is, right? For each L1 norm, we sum over the coordinates of the absolute value differences. And then let me switch the order of summation. So the first summation is over the coordinates, and the second summation is over all the points in the rows, in the kth row. Now, the key idea is that if you can compute this inner sum fast, right, then there's only d of these sums you need to compute. So if you compute each of these sums, really fast, then that's like the main challenge. Okay, so what is the full algorithm? The pre-processing step, we take our points, our data set, and along each coordinate, we're going to sort all these points. And then now to compute this inner sum that's highlighted in yellow, you can actually pre-compute all the answer based on the sorted order. Now, why is that, right? Because this this x sub k of t is fixed, right? So all we're doing is for all the x sub j of t's that are smaller, we're going to sum them up, and then add a negative sign in front of the sum. And for all the things that are bigger, we're going to sum them up and add a positive sign, right? So by computing these prefix sums along the sorted order, we can compute each of these answers in like all of one time. Just that computing the prefix sum and sorting takes some preprocessing. But the key is that we can use this preprocessing now for every row. We can use the same preprocessing. And that's basically the full algorithm. It's very simple to implement, and there's some experiments along that in a bit. Yeah, so that concludes this L1 upper bound result. If there are any questions, I'd be happy to take them.
So maybe one natural question would be, what happens when D is bigger than N? But I think something you sort of hinted at the beginning, saying that it could be extended to polynomial kernels, something like that.
Yeah. So if D is bigger than N, then I'm not sure what to do for the exact case. In general, a lot of times when D is bigger than N, people do like dimensionality reduction, I guess. But I know that in a lot of NLP tasks, D is much bigger than N. Yeah, so this wouldn't work so well in that case. The polynomial kernel stuff is basically about, instead of having an L1 distance function, what if it was like a kernel? It was a kernel matrix, and that for that. Sorry.
Will be closer to an L2 distance in the case of kernels, or you have an L1 again?
So for the L2 case, you can actually get an L2 case straight from the L1 case if you allow a small approximation. And the reason is that L2 embeds into L1 almost exactly. And what is the embedding? You just take your points, you apply a random rotation, and it turns out that the L1 distance after the rotation is roughly the same as the L2 distance before. So now you can just use the L1 algorithm after the rotation. The rotation is fast to apply. So you can actually get an L2 algorithm from the L1 algorithm.
Okay.
And anything that embeds into L1 is Yeah, you can do it. And that's why this L infinity case is really interesting, because it turns out, like, philosophically, L infinity is the hardest metric, because everything sort of embeds into L infinity, but L infinity doesn't embed into anything else. So, like, ideally, if you had an algorithm for L infinity, it would just imply a bunch of new results. But in a lot of cases, right, like the nearest neighbor search case, L infinity, there's actually some lower bounds. And in particular for our matrix vector product case, the theorem says a bunch of words that are not like too important, but essentially it's saying you need n squared time, assuming something called the strong exponential time hypothesis. And how does this proof go? The proof here is also really simple. So we're gonna reduce something called the orthogonal vectors problem to this L infinity case. So first, what is the orthogonal vectors problem? The problem is the following. We have two sets of binary vectors, and we just want to check if there's one vector in the first set and another vector in the second set, such that they're orthogonal with each other. And one of the classical fine-grained conjectures is that this orthogonal vectors problem requires n squared time. So we're going to assume that, and now given that, we're going to say if this requires n squared time, then this L infinity case also requires n squared time. Yes. Sorry, someone raised their hand.
Hey, yeah. One question before you go on to the orthogonal vector analysis. So wait, just so I understand correctly, for the last slide,
Oh yeah.
We're keeping the sorted values? Is this an independent sort of subproblem for every row of A? Because we're computing A sub y or A y sub A.
It turns out that first you sort your points along every coordinate, and then you can use the same sorted thing for every row. But every row is actually computing something different, but it uses the same sorted order. Okay,
cool.
Yeah,
Okay, yeah. And follow-up question, main question here is, do you know of any interesting applications in this case? If we're like updating points, these values dynamically, like you could obviously keep this sort of like prefix sum in like some dynamic version, but are there interesting questions this applies to? Or is this
I guess the data structure here is like really simple. It's just like sorted array, so it's very easy to update. I do think there are like interesting dynamic questions. Maybe, I guess I haven't thought too much about it, but I guess that's a good question to think offline there.
Yeah, no problem. The only thought here was that like a segment tree or something, you could update these prefix sums faster than recomputing.
Right.
Okay, thanks.
Cool. So I was saying, it's sort of classically assumed, or a lot of people assume, that this orthogonal vector problem takes n squared time. And just to remind everyone, we just need to find a pair of orthogonal vectors, one in the first set, second the second set of vectors too, so that they are orthogonal. Okay, so now we're going to reduce orthogonal vectors to L infinity distance matrix computations. And all this means is that if there was an algorithm that could do L infinity matrix vector products fast, we could actually solve orthogonal vectors fast. And that would imply the right direction for the reduction, right? Because orthogonal vector is thought to be hard. So the reduction isn't that, it's pretty short, but it's a bit tricky to think about. So I'll give it in steps. First, we're going to define two functions, f and g. And f will be applied to the vectors x in our orthogonal vector problem. And g will be applied to the vectors y in the orthogonal vectors problem. And it doesn't really matter what f and g are, except we fix two of their values. The first is that f of 0 and g of 0 are both 1/2. The second is that f of 1 is 0, but g of 1 is 1. So it's kind of anti-symmetric in some sense. And we're going to apply f and g to coordinate-wise to all the points in x. So f applies to all the points in x coordinate-wise, and g applies to all the points in y coordinate-wise. And that gives us some new transform vectors. So the key idea is now, okay, let's say we have some x in x and y in y. After the transformation, if the L infinity distance was 1, then the original inner product was greater than 0. And why is that? Because if the only way the L infinity distance can be 1 is that if they're both 1 in some coordinate. And if they're 1 in some coordinate, then the inner product is at least 1, because they're binary vectors. The other case is that if the L infinity distance after the transformation was 1/2, then it actually implies that they were orthogonal before. And the reason is that the only way the L infinity distance can be 1/2 is if one coordinate was 1 and the other coordinate was 0. So this is like the hard part to think about. At least it was for me. Right. But if you believe line 3 that these conditions hold, then it's kind of immediate to see that if you could query this L infinity matrix, basically if you query the all ones vector, it tells you whether all the entries are 1 or there's some entries that's 1/2, some entry that's 1/2, right? Because either the sum is n squared or the sum is a little bit less than n squared, and it tells you what case you're in. So it actually allows you to solve this orthogonal vector problem exactly. So I didn't give the full reduction, because this is a cross distance matrix, but you can massage it to be the same distance matrix as well. But this is like the core idea that the L infinity distance actually certifies something for the orthogonal vectors problem. And that's the entire proof. Okay, so before I present other theoretical results, I'll talk about some experiments. Yeah, and then if anyone has any questions, please feel free to ask. Okay, cool. So now I'll talk about some experiments. I guess, this is my third week here, and people keep talking about Google scale experiments, but these are definitely not Google scale because I did it in my personal laptop, but I think they could be pretty easily. Okay, so these are our data sets. N means the number of points, D is dimensions, and everything will be for the L1 distance function. And in particular, we'll test how fast our L1 algorithm is versus the naive way to do it. So interestingly, for this last data set, the data set itself is very tiny. You can store it in 0.3 megabytes. You can even store it on your phone. But if you actually made the distance matrix A, it takes 5.8 terabytes. And that's really expensive to store. That's more than hard drives in most computers. Right, and then the two things we'll compare is our algorithm, which means the one I presented a bit earlier for the L1 distance matrix case, and the naive algorithm. Naive is either we compute I'll give for naive algorithm I'll give it the benefit of the doubt of having the matrix if it's small enough to store. And then, it'll compute A times Y using a linear algebra library. So it's really optimized. Or, if it's too big, I use some optimized loop to compute A on the fly and then compute A times Y. And that's really for the last case because you can't really store this distance matrix anyways. Okay, so these are the results. So kind of the two things to look at is the pre-processing time. For these smaller data sets, the pre-processing time is the time to create the matrix. And the query time is to compute A times Y. For us, the pre-processing time is to do this sorting thing I talked about. So for this last larger data set, right, there's no pre-processing for the naive algorithm because I couldn't make the distance matrix. It's too big. For us, it's very fast, 16 seconds. And the query time for us is very fast, too. It's 3 seconds. So we can query A times Y, where A is this huge matrix, right? It's million by million matrix. And yeah, the naive algorithm of actually computing on the fly didn't run for a long time, and I had to do a smaller scale problem to estimate how long it will take. And roughly it takes at least 2 days. So there's some definitely big savings here, and it makes sense, right? One is a linear time algorithm, the other is doing something n squared. Cool. All right, so this is the end of the experiments. If anyone has any questions, I'd be happy to talk more. Okay, cool. Okay. So now I'll talk about the final piece of the theoretical result, which is let's say that someone said, okay, I need you to create this distance matrix. I like it. I don't care if it's expensive, just create this matrix. What is the fastest way to do this, right? And this is a previous slide where I said, sort of the most natural way, at least for the L2 case, is to use this Johnson-Lindenstrauss lemma, and you get an n squared log n time to get approximately the same matrix where each entry has some small relative error. But it's actually possible to get a better bound. It's a very funny bound. It's n squared log n, but it's still better than this JL bound, which I think is interesting. Okay, so if you design geometric algorithms, turns out there's only one trick in the book. it's not Chebyshev polynomials. And so this is like apparently a famous code by a famous computer scientist, but it's actually something called a quad tree, which is a data structure that shows up all over the place in geometric algorithms. And if you read papers on geometric algorithms, like a lot of them are just like using this quad tree in very nice and interesting ways. So what is the super high level idea? So first, the idea is to sort of get a compressed representation of every point. And how we do that is we just round it to a very fine grid cell, right? If the grid is really fine enough, right, we can round it to a grid representation, and we're not going to lose much. We're not going to have much error if we round it to a fine enough grid. And the other second idea is that you can actually this grid can be represented using a quad tree. So a quad tree is like a hierarchical tree structure. And the way it works is that, you have a root node, which represents a big box, and the children node represents like smaller sub boxes inside, and you can recurse. This is like the 2D version, but you can imagine in D dimensions what it looks like. This picture isn't that accurate because not only do we want it to like be a quad tree, but we actually want it the grid to be really fine. So we need to make the tree a little bit longer, a little bit deeper. But this is a nice image I found online, and I didn't want to make my own, so this is what we'll go with. Okay, so there's some prior work which says that this compressed representation actually doesn't lose any guarantees. Like this compressed representation is good enough, right? If you round it to something really fine grid, it makes sense that we don't lose any accuracy. But now we have this nice tree data structure that sort of represents all our points. And our goal is to save computation by computing many distances at once, right? Like somehow the tree will help us compute many things, like save computation overall. So again, like this is a very, very high level, like, no formal details, but just to kind of convey to you what's going on is we're going to sort of traverse this tree now. And as we go up and down the tree, we're going to update the representation of the current cell we're in. And it's very easy to do that, right? If you think about what the quad tree is representing, we can update the representation. And the key idea is that we don't need to be storing many points. We need to be storing very few bits while we're going up and down this tree. And turns out like even like constant number of bits per coordinate, essentially. And the reason is like, okay, say you want to compute the distance between this green X and all the other points in this purple subtree, right? You don't really have to store any information that's beyond the purple subtree, right? Because everything is shared by all the points in the subtree. So you don't need to store anything before. And you need to store, and if you travel far enough, like even in the purple subtree, you don't need to store much information. And the reason is, if the green point, that's X, and a red point, if they're already very far apart, we don't need to compute super fine representations of them. Like they're already very far apart, right? So one can use some very coarse representations of both of them to compute the distance accurately. So it turns out that as we go up and down this tree, you need to be keeping track of very, very, very few bits. And because only few bits are here, you can sort of pre-compute all possible answers because you're only representing very few bits. So again, this is at very, very high level, so no formal details. But essentially, this is kind of what's going on. You can save a lot of space and thus computation by representing things in this compressed format. So no details, but hopefully some ideas were conveyed. Cool. So there are some other results that I didn't cover. Basically, we have some fast matrix vector products for other functions, like some polynomial kernels, some more complicated distance functions, but they essentially use this sorting or some kind of linearization idea. We also have some results on fundamental limits of any algorithm which computes matrix vector products. Essentially, there's some evidence about what kind of functions enable you to compute these matrix vector products fast. And something I really didn't cover is downstream applications. So now we have all these matrix vector products that are fast. What does that mean? So it actually implies some of the fastest low-rank approximation results for many distance functions. So for example, for this L1 distance function, there was prior work that said how many queries, how many matrix vector product queries do you need to compute this low rank approximation? And that was like really optimized. But now we have fast matrix vector products, so then you can just plug it in and get some really nice bounds. Yeah, the paper is not out yet, but if you're interested, just email me for the. If you email me, I'm happy to share it. All right, so okay, so this was a lot shorter than I thought, but I have some final parting words, which is what is the impact of this work, or what is next that we can think about? So, and a question that's personally interesting to me is what other dense matrices naturally occur in in the wild. For example, like random matrices are dense. A lot of people think they're natural and they occur in a bunch of places. Or other families like kernel matrices and so on. And how can we design algorithms for them that are scalable? And this is like a very natural direction that seems promising. Yeah, so this is the last slide I have. So thank you for listening, and I'm happy to answer any questions.
So if no one is asking questions, let me ask you one. I was like a curiosity related to your quad-tree or whatever bidimensional representation of. I was wondering, since I'm not completely familiar, maybe with the literature itself, this is independent of whether the tree, so the claim result, whether the tree is balanced or not balanced, etc. Right?
Yeah, it's independent of that. Yeah.
Okay. This is not. Can you perhaps give an intuition about why is that the case? Maybe it's your course delve deeper into.
Yeah. So, right. Yeah.
Because if I understand correctly, the scattering of the data will determine somehow the shape of this tree, right?
Yeah. So the shape of the tree doesn't matter so much. The reason is like let's say that tree was very unbalanced, and there's like one part that's like really long, right? It's a very long tree.
Right.
But what does that mean, right? That means there aren't many points in this part of the tree, right?
Yeah.
And that means like you don't need to keep all these like levers of the tree. You can sort of compress the tree more. You can just say, oh, because the whole point of the tree is to compute distances, and that means there's some points that are just like far away from everything else. So you don't need to. You only need to keep like very coarse representation of them. You don't need to keep this very long tree. You can actually shorten a very long path. So yeah, so there's these kind of details that go in this tree construction that I didn't cover.
Thank you.
Yeah.
Yeah, I guess if there are no other questions, let's thank the speaker.